Welcome back, everyone. Hope you had a good Thanksgiving. Actually, not sure why I have these chairs here. All right, let's get rid of these. By the way, not sure if, thanks, Anand. Not sure if you guys are following the news, but in reinforcement learning, we chat a lot about robotics, right? And one of the, cluster problem a lot of people use reinforcement learning to solve is robotics. And I think back in May, the InSight Mars lander had launched from here in California and is about to make an attempt at landing on the planet Mars in the next 2.5 hours or so. So excited about that. I think it's actually one of the grandest applications of robotics because, with a 20-minute light speed from Earth to Mars, once it starts its landing, there's nothing anyone on Earth can do. And so I think it's actually one of the most exciting applications of autonomous robotics. We launched this thing, is now about 20 light minutes away from planet Earth, so you actually can't control it in real time. And you just have to hope like crazy that your software works well enough for it to land on this planet, and so we'll find out a little bit afternoon if the landing happens successfully or not. Right? I don't know. I think, sorry, I just get excited about stuff like this. I hope you guys do too. And for those of you that are from California, I mean, take some pride that it launched from a home state of California and is now nearing its landing on Mars. Okay. All right. So what I want to do today is continue our discussion on reinforcement learning. Do a quick recap of the MDP, or the Markov Decision Process Framework. And then we'll start to talk about algorithms for solving MDPs. In particular, need to define something called the value function, which tells you how good it is to be in different states of the MDP. And then we'll define the value function and then talk about an algorithm called value iteration for computing the value function. And this will help us figure out how to actually find a good controller or find a good policy for an MDP. And then we'll wrap up with learning state transition probabilities and how to put all this together into an actual reinforcement learning algorithm that you can implement. To recap, our motivating example, a running example from the last time, from before Thanksgiving, was this 11-state MDP. And we said that an MDP comprises a 5-tuple, a list of 5 things, with states. So that example had 11 states, actions, and in this example, the actions were the compass direction north, south, east, and west. You can try to go in each of the 4 compass directions. The state transition probabilities, and in the example, if the robot attempts to go north, it has an 80% chance of heading north and a 0.1% chance of veering off to the left and a 0.1 chance of veering off to the right. Gamma is a number slightly less than 1, usually slightly less than 1. There's a discount factor. Think of this as 0.99. And R is the reward function that helps us specify where we want the robot to end up. And so what we said last time was that the way an MDP works is you start off in some state S0, well, it's much better. You choose an action, A0, and as a result of that, it transitions to a new state, S1, which is drawn according to P of S0, A0. And then you choose a new action, A1, and as a result, the MDP transitions to some new state, P of S1, A1. And the total payoff is this sum of rewards. Right? And the goal is to come up with a way, and formally the goal is to come up with a policy, pi, which is a mapping from the states to the actions, that will tell you how to choose actions from whatever state you're in, so that the policy maximizes the expected value of the total payoff. Okay? And so I think last time I kind of claimed that this is the optimal policy for this MDP. Right? And what this means, for example, is if you look at this state, this policy is telling you that pi of 3, 1 equals west, I guess. Or you can write west or left, or what do you call that? Left arrow, right? Where from this state, from the state 3, 1 the best action to take is to go left, is to go west. And so if you're executing this policy, what that means is that on every step, the action you choose would be, pi, right, of the state that you're in. Okay. So what I'd like to do is now define the value function. So how did I come up with this, right? What I'd like to do is have you learn, given an MDP, given this 5-tuple, how do you compute the optimal policy, right? And one of the challenges with finding the optimal policy is that there's an exponentially large number of possible policies, right? If you have 11 states and 4 actions per state, the number of possible policies is 4 to the power of 11, which is not that big because 11 is a small MDP, right? Because the number of possible policies for an MDP is combinatorially large. It's a number of actions to the power of a number of states. So how do you find the best policy? Okay. So what you learned today is how to compute the optimal policy. Now, in order to develop an algorithm for computing an optimal policy, we'll need to define 3 things. So just as a roadmap, what I'm about to do is define V pi, V star, and pi star, okay? And based on these definitions, we'll see that we'll come to a definition, or we'll derive that pi star is the optimal policy, okay? But so let's go through these few definitions. First, V pi. So for policy pi, V pi, this is a function mapping from states to the rails, is such that V pi of s is the expected total payoff for starting in state S and executing pi. And so sometimes you write this as V pi of S is the expected, total payoff given that you execute the policy pi and the initial state S0 is equal to S. Okay? So the definition of V pi, this is called the value function for a policy. Right? Or this is called the value function for the policy pi. Okay? And so what the value function for policy pi, denoted V pi is it tells you for any state you might start in, there's a function mapping of states to rewards, right? For any state you might start in, what's your expected total payoff if you start off your robot in that state and if you execute the policy pi? And execute the policy pi means take actions according to the policy pi. Right? So here's a specific example. This policy, so let's consider following policy pi, right? So this is not a great policy, right? From some of these states, it looks like it's heading to the -1 reward. Oh, sorry, so remember the reward was +1 if you get here. And technically, this is called an absorbing state, meaning that if you ever get to the +1 to the -1, then the world ends and there are no more rewards or penalties after that, right? So this is actually not a very good policy. So policy is any function mapping from the states to the actions. So this is one policy that says in this state, this policy tells you in this state 4-1, go north, which is actually a pretty bad thing to do, right? It's take you to the -1 reward. So this is not a great policy, but this is just a policy. And V pi for this policy looks like this. Don't worry too much about the specific numbers, but if you look at this policy, you see that from this set of states, it's pretty efficient at getting you to the really bad reward, and from this set of states, it's pretty efficient at getting you to the good reward, right? With some mixing because of the noise in the robot veering off to the side, and so, these numbers are all negative, and those numbers are at least somewhat positive, right? So V pi is just if you start from, say, this state, from the state 1, 1, on expectation, your expected sum of discounted rewards will be negative 0.88, okay? So that's what V pi is, right? Now, the following equation, let me think, governs the value function. Right, it's called Bellman's equation. And this says that your expected payoff at a given state is the reward that you receive plus the discount factor times the future reward. So let me actually explain the intuition behind this, right? Which is that let's say you start off at some state S0, right? So and again, let's say S is equal to S0, right? So V pi of S is equal to, well, just for your robot waking up in that, I'm going to add this in a second, okay? But just for the fact that your robot woke up in this state S, you get the reward R of S0 right away. This is also called the immediate reward, right? Because just for the good fortune or bad fortune of starting off in this state, the robot gets a reward right away. This is called the immediate reward. And then it will take some action and get to some new state S1 where it'll receive, gamma times the reward of S1. And then right? And then it'll get some future reward at the next step and so on. And just to flesh out the definition, the value function V pi is really this, given that you execute the policy pi and S0 equals S, right? And you start off in the state S0. Now, what I'm going to do is rewrite this part of the equation a little bit. I'm going to factor out, I'm just going to take the rest of this and factor out one factor of gamma. So let me put parentheses around this, right, and just take out gamma there, okay? So I'm just, taking this, previously this was gamma squared, right? But adding the parentheses here, I'm just taking out one factor of gamma that multiplies in the rest of that equation, okay? Does this make sense? No, so as in gamma R of S1 plus gamma squared R of S2 plus dot 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 equals gamma times R of S1 plus. Okay, so that's what I did down there, right? Just factor out one factor of gamma. And so this is the value of state S is the immediate reward plus gamma times the expected future rewards, right? So this, the expected value of this is really V pi of S1, right? So this, and so the second term here, this is the expected future rewards. Right? So Bellman's equation says that the value of a state, the expected total payoff you get if your robot wakes up in the state S is the immediate reward plus gamma times the expected future rewards. Okay, right? And this thing under above the curly braces is really asking if your robot wakes up at the state S1 and executes pi, what is the expected total payoff, right? And this, well, if your robot wakes up in state S1, then it'll take an action, get to S2, take an action, get to S3, and this is the sum of discounted rewards for if it starts off in the state S1. Okay? Make sense? So, based on this, you can write out, well, at least justify Bellman's equations, which is, excuse me, and the mapping from this equation to this equation the mapping from the equation on top to the equation at the bottom is that S maps to S0 and S prime maps to S1, right? Right. And so if we have that V pi of S equals make sense? Right. So the value of state S is R of S plus V pi of S prime, where this is really S0, and this is S1. And in the notation for MDP, if you want to write a long sequence of states, we tend to use S0, S1, S2, S3, and S4, and so on. But if you want to look at just the current state and the state you get to after one time step, we tend to use S and S prime for that. So that's why there's this mapping between these two pieces of notation. So if S prime is the state you get to after one step, well, let's see. What is S prime drawn from, right? So the state S prime or S1 is the state you get to after one time step. So what is the distribution that S prime is drawn from? S prime is drawn from P of what? Yep, okay, P of S, and then pi of S, right, cool. That makes sense? Because in state S, you will take action A equals pi of S, right? So we're executing the policy pi. So that means that when you're in a state S, you're going to take the action A given by pi of S, because pi of S tells you, please take this action A when you're in state S. And so S prime is drawn from P of SA, where A is equal to pi of S, right? Because that's the action you took, which is why S prime, the state you get to after one time step, is drawn from distribution S pi of S. Okay? Wow, that pen really left a mark. Oh. So putting all that together, that's why, well, I'll just write that again. We're Bellman's equations, which is V pi of S equals R of S plus the discount factor times the expected value of V pi of S prime. And so this term here is just sum of S prime V S pi of S V pi of S prime. Okay, so that underlying term, I guess, is this underlying term here. Okay. Now, notice that this gives you a linear system of equations for actually solving for the value function. So let's say I give you a policy. Right? It could be a good policy, it could be a bad policy, and you want to solve for V pi of S. What this does is, if you think of V pi of S as the unknowns you're trying to solve for, given pi, right, these equations the Bellman's equations defines a linear system of equations in terms of v pi of s as the values to be solved for. So here's a specific example. Let's take the state 3, 1. Right, so this is the state 3, 1. Okay? What Bellman's equations tells us is v pi of the state 3, 1 is equal to the immediate reward you get at the state 3, 1 plus the discount factor times, well, sum of s prime p s pi of s v pi of s prime, right? So, and let's see. Let's say that pi of 3, 1 is north, right? So let's say you try to go north. If you try to go north from this state, then you have a 0.8 chance of getting to 3, 2 plus a 0.1 chance of veering left plus a 0.1 chance of veering right. Let me just close out that parenthesis. Okay, so that's what Bellman's equation says about these values, right? And if your goal is to solve for the value function, then these things I'm just circling in purple are the unknown variables, right? And if you have 11 states, like in our MDP, then this gives you a system of 11 linear equations with 11 unknowns. And so using sort of a linear algebra solver, you could solve explicitly for the value of these 11 unknowns. Does that make sense? Right? So the way you would, so let's say I give you a policy pi, any policy pi. The way you can solve for the value function is create an 11-dimensional vector with v pi of, 1, 1, v pi of 1, 2, and so on, down to v pi of whatever is the last state. You have 11 states, so v pi of 3, 3 or whatever, 4, 3. Right? So if you want to solve for those 11 numbers that I wrote up just in terms of defining v pi, what you can do is I'll give you a policy pi. You can then construct an 11-dimensional vector, 11-dimensional vector of unknown values that you want to solve for. And Bellman's equations for each of the 11 states, for each of the 11 states you could plug in on the left-hand side. This gives you one equation for how one of the values is determined as a linear function of a few other of the values in this vector. Okay? And so what this does is it sets up a linear system of equations with 11 variables in 11 unknowns. Right? And using a linear algebra solver, you will be able to solve this linear system of equations. Does this make sense? Okay. All right. And so this works so long as you have a discrete, if you have 11 states, it takes like takes almost no time, right, in a computer to solve a linear system of 11 equations. So that's how you would actually get those values if you ever called on to solve for v pi. Okay. Actually, did what I just say make sense? Raise your hand if what I just explained made sense. Okay, cool, awesome, great. Good. So moving on our roadmap, we'll define v pi. Let's now define v star. So So V star is the optimal value function. And we'll define it as V star of S equals max over all policies pi of V pi of S. Okay? One of the, I don't know, slightly confusing things about reinforcement learning terminology is that there are two types of value function. There's value function for a given policy pi, and that's the optimal value function V star. So both of these are called value functions, but one is a value function for a specific policy. It could be a great policy, it could be a terrible policy, it could be the optimal policy. The other is V star, which is the optimal value function. So V star is defined as look at the value for any, look across all of the possible policies you could have, all 4 to 11, right? All the combinatorially large number of possible policies for this MDP. And V star of S is, well, let's just take the max, right? Which is of all the policies anyone could implement, of all the possible policies, let's take the value of the best possible policy for that state. So that's V star. Okay, and that's the optimal value function. And it turns out that there is a different version of Bellman's equations for this. And again, there's a Bellman's equations for V pi, for value of a policy, and then there's a different version of Bellman's equations for the optimal value function, right? So just as there are two versions of value functions, there are two versions of Bellman's equations. But let me just write this out, and hopefully this will make sense. Actually, let's think this through. So let's say you start off your robot in a state S. What is the best possible expected sum of discounted rewards? What's the best possible payoff it could get, right? Well, just for the privilege of waking up in state S, the robot will receive an immediate reward R of S, right? And then it has to take some action. And after taking some action, it will get to some other state S prime, and after some other state S prime, it will receive, right, future expected rewards, V star of S prime, and we have to discount that by gamma, right? So, well, the state S prime was arrived at by your taking some action A from the initial state. And so whatever the action is, for if you take action A, right? Okay. So if you take an action A in the state S, then your total payoff will be, expected total payoff will be the immediate reward plus gamma times the expected value of the future payoff. But what is the action A that we should plug in here, right? Well, the optimal action to take in the MDP is whatever action maximizes your expected total payoff, maximizes the expected sum of rewards, which is why the action you want to plug in is just whatever action A maximizes that. Okay? So this is Bellman's equations for the optimal value function, which says that the best possible expected total payoff you could receive starting from state S is the immediate reward, R of S, plus max over all possible actions of whatever action allows you to maximize, your expected total payoff, expected future payoff. Okay, so this is the expected future payoff, or expected future reward. Now, based on the argument we just went through, this allows us to figure out how to compute pi star of S as well, right? Which is, let's say we have a way of computing V star of S, right? We don't yet, but let's say I tell you what is V star of S, and then I'll ask you, what is the action you should take in a given state? So remember, pi star is going to be optimal policy. Right? And so what should pi star of S be, right? Which is, let's say we're a way of computing V star, and I now ask you, hey, my robot's in state S, what is the best action I should take from the state S, right? Then how do I decide what action to take in the state S? What do you think is the best action to take from this state? And the answer is almost given in the equation above, right? Yeah. Yeah, cool, awesome, right? So the best action to take in state S, and best means maximizing your expected total payoff. But the action that maximizes your expected total payoff is, well, whatever action we were choosing A up here, and so it's just argmax over A of that. And because gamma is just a constant that doesn't affect the argmax, usually we just eliminate that since it's just a positive number, right? So this gives us the strategy we will use for finding the optimal policy for an MDP, which is we're going to find a way to compute V star of S, which we don't have a way of doing yet, right? V star was defined as a max over combinatorially or exponentially large number of policies, so we don't have a way of computing V star yet. But if we can find a way to compute V star, then using this equation, sorry, let me just scratch this out. Okay. Using this equation gives you a way for every state S to pretty efficiently compute this argmax, and therefore figure out what is the optimal action for every state. Okay. All right. So just to practice with confusing notation. All right, let's see if you understand this equation. I'm just claiming this, I'm not proving this. But for every state as V star of S equals V of pi star of S is greater than V pi of S, right? For every policy pi in every state S, okay? So I hope this equation makes sense. This is what I'm claiming. I didn't prove this. What I'm claiming is that the optimal value for state S is, this is the optimal value function on the left. This is the value function for pi star. So this is the optimal value function. This is the value function for a specific policy pi, where the policy pi happens to be pi star. And so what I'm claiming here is that, what I'm writing here is that the optimal value for state S is equal to the value function for pi star applied to the state S, and this is greater than or equal to V pi of S for any other policy pi. Okay? Right. All right. So the strategy you can use for finding for optimal policy is one, find V star. Two, use the argmax equation to find pi star. Okay. And so what we're going to do is, step two, right, we know how to do from the argmax equation. So what we're going to do is talk about an algorithm for actually computing V star, because if you can compute V star, then this equation allows you to pretty quickly find the optimal action for every state. So, so value iteration is an algorithm you can use to find V star. So let me just write out the algorithm. So this is okay. So in the value iteration algorithm, you initialize the estimated value of every state to 0, and then you update these estimated values using Bellman's equations. And this is the optimal value function, the V star version of Bellman's equations. Right? And so to be concrete about how you implement this, if you're implementing this, right? If you're implementing this in Python, what you would do is create an 11-dimensional vector to store all the values of V of S. So you create a 11-dimensional vector, right? That represent V of 1, 1, V of 1, 2, down to V of 4, 3, right? So this is 11-dimensional vector corresponding to the 11 states. Oh, I'm sorry. Wait, did I say 11? We have 10 states in the MDP, don't we? Wait. Yes, we have 10 states. I've been saying 11 all along. Sorry. Okay, 10. Yeah. Wait. 11? Oh, yes, you're right. Sorry. Yes, 11. Okay. Sorry. Yes, 11 states. Okay, sorry, right. So 11 states in MDP. So you create an 11-dimensional vector and initialize all of these values to 0. And then you will repeatedly update the estimated value of every state according to Bellman's equations, right? And so there are actually two ways to interpret this. And similar to gradient descent, right? We've written out, a gradient descent rule for updating the theta, the vector parameters theta. And what you do is, and what you do is you update all of the components of theta simultaneously, right? And so that's called a synchronous update in gradient descent. So the way you would update this equation in what's called a synchronous update would be if you compute the right-hand side for all 11 states, and then you simultaneously overwrite all 11 values at the same time. And then you compute all 11 values for the right-hand side, and then you simultaneously update all 11 values, okay? The alternative would be an asynchronous update. And in an asynchronous update, what you do is you compute V of 1, 1, right? And the value of V of 1, 1 depends on some of the other values on the right-hand side, right? But in an asynchronous update, you compute V of 1, 1, and then you would overwrite this value first, and then you use that equation to compute V of 1, 2, and then you update this, and then you sort of update these one at a time. And the difference between synchronous and asynchronous is, if you're using asynchronous update, by the time you're using V of 4, 3, which depends on some of the earlier values, you'd be using a new and refreshed value of some of the earlier values on your list, okay? It turns out that value iteration works fine with either synchronous updates or asynchronous updates, but because it vectorizes better, because you can use more efficient matrix operations, most people use a synchronous update. But it turns out that the algorithm will work whether you use a synchronous or an asynchronous update. So I guess unless otherwise stated, you should usually assume that when I talk about value iteration, I'm referring to synchronous update, where you compute all the values, all 11 values, using the and then update all 11 values at the same time. Okay, was there a question just now? Someone had that, yeah.
So in our specific MDP, we also have these two sync states where if you got there, the simulation ended. Would we represent that by saying that like the transition probability from node to any other state is 0?
I see.
Or is there a way to kind of like hard code, oh actually we don't want to maximize over any subsequent states when we reach that terminal?
Yeah, yes. So I think yes. So how do you represent the absorbing state, the sync state? We get to +1, -1, then the world ends. In this framework, one way to code that up would be to say that the state transition parameter from that to any other state is 0. That's one way that will work. Another way would be done less often, maybe mathematically a little bit cleaner, but not how people tend to do this, would be to take your 11-state MDP and then create a 12th state, and the 12th state always goes back to itself with no further reward. So both of these will give you the same result. Mathematically, it's pretty more convenient to just set, P of SA S prime equals 0 for all other states. It's not quite a state transition probability, but that will give you the right answer as well. Yeah, thanks. All right, cool. So just as a point of notation, if you're using synchronous updates, you can think of this as taking the old value function, old estimate, right? And using it to compute the new estimates, right? So this assuming the synchronous update, you have some previous 11-dimensional vector with your estimates of the value from the previous iteration. And after doing one iteration of this, you have a new set of estimates. So one step of this algorithm is sometimes called the Bellman backup operator. And so where you update V equals B of V, right? Where now V is a 11-dimensional vector. So you have an old 11-dimensional vector, compute the Bellman backup operator with just that equation there, and update V according to B of V. And so one thing that you see in the problem set is showing that this will make V of S converge to V star. Okay? So it turns out that so it turns out that you can prove, and you see more details of this in the problem set, that by repeatedly enforcing Bellman's equations, that this algorithm will cause your vector of 11 values, so cause V, to converge to the optimal value function V star. Okay? And more details, you see in the homework, a little bit in the lecture notes. And it turns out this algorithm actually converges quite quickly, right? To give you a flavor, I think that with the discount factor, if the discount factor is 0.99, it turns out that you can show that the error reduces by a factor of 0.99 on every iteration. And so V actually converges quite quickly, geometrically quickly or exponentially quickly to the optimal value function V star. And so if the discount factor is 0.99, then with with 100 iterations or a few hundred iterations, V would be very close to V star. Okay? And if the discount factor is 0.9, then with just 10 or a few dozens of iterations, it'll be very close to V star. So this algorithm actually converges quite quickly to V star. Okay. So let's see. So just to put everything together, if you run value iteration on that MDP, you end up with this. So this is V star. Okay? So it's a list of 11 numbers telling you what is the optimal expected payoff for starting off in each of the 11 possible states. And so I had previously said, I think I said last week, the week before Thanksgiving, that this is the optimal policy. Right? So, let's just use as a case study how you compute the optimal action for that state given this V star. Right? Well, what you do is you'd actually just use this equation. And so if you were to go west, then if you were to compute, I guess, this term, sum of S prime, west or left, I guess, right? P of SA S prime, V star of S prime is equal to, if you were to go west, you have a right? So if you're in this state, and if you attempt to go left, then there's a 0.8 chance you end up there with a V star of 0.75. There's a 0.1 chance, if you try to go left, there's 0.1 chance you veer off to the north and have a 0.69. And then there's a 0.1 chance that you actually go south and bounce off the wall and end up with a 0.71. And so the expected future rewards, expected future payoff, given this equation, is that if you attempt to go west, you end up with 0.740 as expected future rewards. Whereas if you were to go north, if you do a similar computation, so 0.8 times 0.69 plus 0.1 times 0.75 plus 0.1 times 0.49, the appropriate weighted average, you find that is equal to 0.676, which is why the expected future rewards for if you go west, if you go left, is 0.740, which is quite a bit higher than if you go north, which is why we can conclude, based on this little calculation, that the optimal policy is to go left at that state. Okay? And really, and technically, you check north, south, east, and west and make sure that going west gives a high reward, and that's how you can conclude that going west is actually the better action at this state. Okay? So that's value iteration, and based on this, if you are given an MDP, you can implement this, solve for V star, and be able to compute pi star. Okay? All right. A few more things I want to go over, but before I move on, let me check if there are any questions. Yeah? Oh, sure. Yep. Its number of states is always finite. So in what we're discussing so far, yes, but what we'll see on Wednesday is how to generalize this framework. I'll allude to this a little bit later, but it turns out if you have a continuous state MDP, one of the things that's often done, I guess, is to discretize into finite number of states, but then there are also some other versions of value iteration that applies directly to continuous states as well. Yeah. Anything else? Okay, cool. All right. So What I described is an algorithm called value iteration. The other, I don't know, common sort of textbook algorithm for solving for MDPs is called policy iteration. And let me just, I'll just write out what the algorithm is. So here's the algorithm, which is, initialize pi randomly, right? Okay. So let's see what this algorithm does. We'll talk about pros and cons of value iteration versus policy iteration a little bit. In policy iteration, instead of solving for the optimal policy V star, so in value iteration, our focus of attention was V star, right? Where you do a lot of work to try to find the value function, and then once you solve for V star, you then figure out the best policy. In policy iteration, the focus of attention is on the policy pi rather than the value function. And so initialize pi randomly. So that means for each of the 11 states, pick a random action, right? So a random initial pi. And then we're going to repeatedly carry out these two steps. The first step is solve for the value function for the policy pi, right? And remember, for V pi, this was a linear system of equations right, with 11 variables, with 11 unknowns, and it was a linear system of 11 equations with 11 unknowns. And so using a sort of linear algebra solver or a linear equation solver, given a fixed policy pi, you could just, at the cost of inverting a matrix roughly, right, you could solve for all of these 11 values. And so in policy iteration, you would use a linear solver to solve for the optimal value function for this policy pi that we just randomly initialize, and then set V to be the value function for that policy, okay? And so this is done quite efficiently with a linear solver. And then the second step of policy iteration is pretend that V is the optimal value function and update pi of S, using the Bellman's equations for the optimal value function, right, or update it as you saw, right, for how you update pi of S. And then you would iterate. And then given a new policy, you then solve that linear system of equations for your new policy pi, so you get a new V pi, and then you keep on iterating these two steps until it converges. Okay? Yeah. Yeah, yep, yes, that's right. So in value, So in value iteration, actually, in value iteration, think of value iteration as waiting to the end to compute pi of S, right? Solve for V star first and then compute pi of S. Whereas in policy iteration, we're coming up with a new policy on every single iteration, right? Okay. So pros and cons of and it turns out that this algorithm will also converge to the optimal policy. Pros and cons of policy iteration versus value iteration. Policy iteration requires solving this linear system of equations in order to get V pi. And so it turns out that if you have a relatively small state space, like if you have 11 states, it's really easy to solve a linear system of equations, of 11 equations in order to get V pi. And so if a relatively small set of states, like 11 states, or really anything, like a few hundred states, policy iteration would work quite quickly. But if you have a relatively large set of states, like 10,000 states or a million states, then this step would be much slower, at least if you do it right by solving linear system equations, and then I would favor value iteration over policy iterations. So for larger problems, usually value iteration will, usually I would use value iteration because solving this linear system of equations, is pretty expensive. If it's like a million equations, a million unknowns, that's quite expensive. But if 11 states, 11 unknowns, this is a very small system of equations. And then one other pros and cons, one other difference that's maybe more academic than practical, but it turns out that if you use value iteration, V will converge toward V star, but it won't ever get to exactly V star, right? So just as if you apply gradient descent for linear regression, gradient descent gets closer and closer and closer to the global optimum, but it never, gets exactly the global optimum. It just gets really, really close really, really fast. Actually, gradient descent actually turns out asymptotically converges geometrically quickly or exponentially quickly, right? But never quite gets, definitively to the one optimal value. Whereas you saw using normals equations, it just jumps straight to the optimal value, and there's no, converging slowly. And so value iteration converges toward V star, but it doesn't ever end up at exactly the value V star. This difference may be a bit academic because in practice it doesn't matter, right? But in policy iteration, if you iterate this algorithm, then after a finite number of iterations, this algorithm will stop changing, meaning that after a certain number of iterations, pi of s will just not change anymore, right? So you find pi of s, update the value function, and then after another iteration, when you take these argmaxes, you end up with exactly the same policy. And so this just solves for the optimal value and the optimal policy, and it just, it doesn't converge. It doesn't just converge to what the optimal value. It just gets the optimal value when it converges. Okay. So I think in practice, I actually see value iteration used much more because solving this linear system equations gets expensive, if you have a larger state space. But value iteration, I see value iteration used much more. But if you have a small problem, I think you could also use policy iteration, which might converge a little bit faster if you have a small problem. Okay. All right, good. So the last thing is kind of putting it together, right? And what if you don't know? Right? So it turns out that when you apply this to a practical problem, in robotics, right? One common scenario you run into is if you do not know what is P of SA, if you don't know the state transition probabilities, right? So when we built the MDP, we said, well, let's say the robot, if you go north, has a 0.8 chance of going north and a 0.1 chance of veering off to the left or right. If you actually, and again, this is a very simplified robot, but if you build an actual robot, or build a helicopter or whatever, play chess against an opponent, the state transition probabilities are often not known in advance. And so in many MDP implementations, you need to estimate this from data. And so the workflow of many reinforcement learning projects will be that you will have some policy and have the robot run around. Just have a robot run around the maze and count up of all the times you had it take the action north, how often did it actually go north and how often did it veer off to the left or right, right? And so you use those statistics to estimate the state transition probabilities. So let me just write this out. So you estimate, so after taking maybe a random policy or take some policy, execute some policy in the MDP for a while, and then you would estimate this from data. And so the obvious formula would be estimate P of SA S prime to be number of times took action A in state S and got to S prime and divide that by the number of times you took action A in state S, right? So P of SA S prime estimate, this is actually a maximum likelihood estimate. Where you look at the number of times you took action A in state S, and of that, what's the fraction of times you got to the state S prime, right? Or 1 over S if the above is 0 over 0, right? And a common heuristic is if you've never taken this action in this state before, if the number of times you try action A in state as is 0, so you've never tried this action in this state, so you have no idea what it's going to do, then just assume that the state transition probability is 1 over 11, right? That it randomly takes you to any state. So this would be common heuristics that people use when implementing reinforcement learning algorithms. Okay? And it turns out that you can use Laplace smoothing for this if you wish, but you don't have to, because so you remember Laplace smoothing, right? So it'd be add 1 to the numerator and add 11 to the denominator would be if you were to use Laplace smoothing, which avoids the problems of 0 over 0s as well. But it turns out that unlike the naive Bayes algorithm, these solvers, the MDPs, are not that sensitive to 0 values. So if one of your estimates were probably a 0, unlike naive Bayes, where having a 0 probability was very problematic for the classifications made by naive Bayes, it turns out that MDP solvers, including valuation and policy iteration, they do not give sort of nonsensical / horrible results just because of a few probabilities that are exactly 0. And so in practice, you can use Laplace smoothing if you wish, but because the reinforcement learning algorithms don't perform that badly, if these estimates are often a little bit over 0, in practice, Laplace smoothing is not commonly used. And what I just wrote is more common. Okay. So to put it together, if I give you a robot and ask you to implement a MDP solver to find a good policy for this robot, what you would do is the following. Take actions with respect to some policy pi. To get experience in the MDP. So go ahead and let your robot loose and have it execute some policy for a while. And then update estimates of PFSA, right? Based on the observations of where the robot goes when it takes different states, get updated estimates of PFSA. Solve Bellman's equation using value iteration. To get V, and then update So this is the value iteration way of putting it together. If you want to plug in policy iteration instead in this step, that's also okay. But so if you actually get a robot, you know, yeah, right. If you actually get a robot where you do not know in advance the state transition probabilities, then this is what you would do in order to iterate a few times, I guess, right? Repeatedly find a policy given your current estimates of the state transition probabilities, get some experience, update your estimates, find a new policy, and kind of repeat this process until hopefully it converges to good policy. Okay? Now, just to add more color or more richness to this, we usually think of the reward function as being given, right, as part of the problem specification. But sometimes you see that the reward function may be unknown. And so, for example, if you're building a stock trading application and the reward is the returns on a certain day, it may not be a function of the state. It may be a little bit random. Or if your robot is, running around, but depending on where it goes, it may hit different bumps in the road. And you want to give it a penalty every time it hits a bump. Well, we build a self-driving car, right? And every time it hits a bump, hits a pothole, you give it a negative reward. Then sometimes the rewards are a random function of the environment. And so sometimes you can also estimate the expected value of a reward. But in some applications, if the reward is a random function of the state, then this process allows you to also estimate the expected value of the reward from every state. And then running this will help you to converge. Okay? Yeah.
When we evaluate, would it make sense once we have the optimal, like for one iteration, we have the optimal policy function, and we start again, would it make sense to check in some error into this policy function to get more exploration? Or
Yeah.
Yep, cool.
Yep, cool, great question. So let me talk about exploration, right? So it turns out that there's one. So it turns out this algorithm will work okay for some problems, but there's one other, again, to add richness to this, there's one other issue that this is not solving, which is the exploration problem. And in reinforcement learning, sometimes you hear the term exploration versus exploitation, right? Which is, let me use a different MDP example, right? Which is, if your robot, starts off here, and if there is a +1 reward here, right, and maybe a +10 reward here, if just by chance, during the first time you run the robot, it happens to find its way to the +1, then if you run this algorithm, it may figure out that going to the +1 is a good way, right? We're giving a discount factor. There's a fuel surcharge of -0.02 on every step. So if just by chance your robot happens to find its way to the +1 the first few times you run this algorithm, then this algorithm is sort of locally greedy, right? It may figure out that this is a great way to get to +1 reward, and then the world ends. It stops getting these -0.02 surcharges for fuel. And so this particular algorithm may converge to a bad, kind of local optima where it's always heading to the +1. And as it hits the +1, sometimes it'll veer off randomly, right? And get a little bit more experience in the right half of the state space and end up with pretty good estimates of what happens in the right half of the state space. And it may never find this hard to define +10 pot of gold over on the lower left, okay? So this problem is sometimes called, it is called the exploration versus exploitation problem, which is when you're acting on an MDP, how aggressively or how greedy should you be at just taking actions to maximize your rewards? And so the algorithm we describe is relatively greedy, right? Meaning that it's taking your best estimate of the state transition probabilities and rewards and it's just taking whatever actions, and this is really saying, you know, pick the policy that maximizes your current estimate of the expected rewards, and it's just acting greedily, meaning on every step, it's just executing the policy that it thinks allows it to maximize the expected payoff, right? And what this algorithm does not do at all is explore, which is the process of taking actions that may appear less optimal at the outset, such as if the robot hasn't seen this plus 10 reward, doesn't know how to get there, maybe it should, you know, just try going left a couple times just for the heck of it, right, to see what happens. Because even if it seems less, even if going left from the perspective of the current state of the knowledge of the robot, maybe if it tries some new things it's never tried before, maybe it'll find a new pot of gold. Okay? So this is called the exploration versus exploitation trade-off. And this is actually not just an academic problem. It turns out that some of the large online web advertising platforms have the same problem as well. Again, I have mixed feelings about the advertising business. It's very lucrative, but it causes other problems as well. But it turns out that for some of the large online ad platforms, you know, when an advertiser starts selling a new ad or, you know, posts a new ad on one of the large online ad platforms, the ad platform does not know who is most likely to click on this ad, right? And so pure exploitation, boy, exploitation is such horrible connotation, especially when we talk about online ad platforms. It's a technical term, not a social term when used in context. But a pure, you know, reinforcement learning sense exploitation policy, not the other, even more horrible sense of exploitation, would be to always just show users the ads that, you know, they are most likely to click on to drive short-term revenues, because we want to just show people the ad they're most likely to click on to drive short-term revenue. Whereas an exploration policy for large, you know, some of the large online ad platforms is to show people some ads that may not be what we think you're most likely to click on in this moment in time, but by showing you that ad or by showing a pool of users an ad that you might be less likely to click on, maybe we'll learn more about your interest, and that increases the effectiveness of these ad platforms at finding more relevant ads, right? I mean, for example, I don't know. Probably not, I guess there are probably no advertisements for Mars landers, as far as I know. But if the large online ad platforms don't know that I'm actually pretty interested in Mars landers, if it shows me an ad for a Mars lander, which I don't think such a thing exists, right, and finds that I click on it, then it may learn that showing me ads for Mars landers is a great thing, right? Or some other thing that it may not know you're interested in. So this is actually a real problem. There are some of the large online ad platforms actually do explicitly consider exploration versus exploitation and make sure that sometimes it shows ads that may not be the most likely you click on, but, you know, allows you to gather information to then be better situated to figure out where the future rewards, to be better positioned to learn how to match ads, not just to you, but to other users like you, right? Sorry, okay. But so in order to make sure the reinforcement learning algorithm explores as well as exploits, a common modification to this would be instead of taking actions with respect to pi, you may have a 0.9 chance with respect to pi and 0.1 chance take an action randomly, okay? And so this particular exploration policy is called epsilon greedy, where on every time step, and on every time step you toss a bias coin, but on every time step, let's say 90% of the chance you execute whatever you think is the current best policy, and with 10% chance you just take a random action. And this type of exploration policy increases the odds that, you know, every now and then, maybe just by chance, right, it'll find its way to the plus 10 pot of gold and learn state transition probabilities and then eventually end up exploring the state space more thoroughly, okay? This is called epsilon greedy exploration, and it's a little bit of a misnomer, I think. So in the way we think of epsilon greedy, epsilon is say 0.1, is the chance of taking a random action instead of the greedy action. This algorithm is always been a little bit strangely named because if 0.1 is actually the chance of you acting randomly, right? So epsilon greedy sounds like you're being greedy 0.1 of the time, but you're actually taking actions randomly 0.1 of the time. So epsilon greedy is actually maybe 1 minus epsilon greedy. So this name has always been a little bit off, but that's how people use this term. Epsilon greedy exploration means epsilon of the time, which is a hyperparameter, which is a parameter of the algorithm, you act randomly instead of according to what you think is the best policy. Okay, and it turns out that if you implement this algorithm with epsilon greedy exploration, then this algorithm will converge to the optimal policy for any discrete state MDP. Right. Sometimes it can take a long time because, if it takes a long time to randomly find plus 10, it could take a long time before it randomly stumbles upon the plus 10 pot of gold. But this algorithm with an exploration policy will converge to the optimal. Will converge the optimal policy for any MDP. Is this your question?
Is there a sense to whether it makes sense to then shrink epsilon after you've explored a lot, or should we always keep epsilon constant?
Oh, yeah, yes, so right. Should you always keep epsilon constant or should you dynamic shrink epsilon? So yes, there are many heuristics for how to explore. One reasonable thing to do would be start with a large value of epsilon and then slowly shrink it. Another common heuristic would be, there's a different type of exploration called Boltzmann exploration that you can look up if you want, which is if you think that the value of going north is 10 and the value of going south is 1, then there's such a huge difference that you should bias your action toward going to the bigger result, the bigger reward, and you could have the probability be e to the value, basically, right? Divided times the scaling factor, right? So that's called Boltzmann exploration, where instead of having a 10% chance of taking action completely at random, you could just have a very strong bias to heading toward the higher values, but also have some probability to going to lower values, but where the exact probability depends on the difference in active values. So I think epsilon greedy, I feel like I see this used the most often for these types of MDPs, and then Boltzmann exploration, which is why I just described, is also used. Wow, just 2 more questions to wrap up. Go ahead.
Can you also give a reward for reaching states you've never seen before?
Oh. Yes, can you give a reward for reaching states you've never seen before? Yes, there's a fascinating line of research called intrinsic reinforcement learning. I think it really started by Satinder Singh. If you Google for intrinsic motivation, you find some research papers on, and then there was some recent follow-on work, I think by DeepMind or some of the groups, but intrinsic motivation is the term to Google, where you reward a reinforcement learning algorithm for finding new things about the world. This one last question? Wait, sorry, say that again? Oh, I see, right. How many actions should you take before updating pi? There's no harm to doing it as frequently as possible. If you're doing this with a real robot, what I've seen is this is sometimes going to a physical robot, and so I don't know, when I fly helicopters, you go out to the field for a day, collect a lot of data, and then go back to the lab in the evening and rerun the algorithms. But if there's no barrier to running this all the time, then it doesn't hurt the performance. It just run it as frequently as you can. All right, that's it for basics of MDP. On Wednesday, we'll continue with generalizing all these to continuous state MDPs. Okay, let's break. We'll see you on Wednesday.